Okay. So I have all this stuff on the board, so I can actually explain it without having to rewrite it all. So the first line is f of x as a power series. So if we're going to say we can represent this function as a power series, that's what that means. Remember, it was basically everything in the exponent continues to go up over and over again. That's basically what we looked at last class. So anything I can represent as a power function, that's what it is. That's the summation that goes on forever. Towards the end of last class, what we looked at was we can start taking the derivatives of those. So if I took the derivative of it, remember derivatives, constant terms disappear. That's gone. The one through the first power, that disappears. The constant stays. The exponent comes down. You have the 2 down, the 3 down, the 4 down, 5, and it keeps going. So my first coefficient is basically just whatever the coefficient is. It's that 1. Sure. We did the derivative at the very end. I did derivative and I did interval. We took the derivative of both sides because that's how I figured out the ln of 1 over 1 minus x. Because that was the same as the derivative of 1 over 1 minus x. All right. So the real thing that I want you to look at is, do you look for a pattern that's forming as we keep going? So what do you notice is happening with the coefficients as we keep going? But how are they increasing? So it was 1, now 2, then 2 times 3. This one's 2 times 3 times 4. This one's 3 times 4 times 5. If I did this one again, what's going to be in front of the 3? We did the derivative of this piece right here again. The 2 would come down right in front, right? And the next one will be a 1 down in front. So what thing do we have that's going to give me something that's 1 times 2 times 3 times 4 times 5 times whatever? The factorial. So in essence, what we're looking at here is these pieces here ends up becoming a factorial. So my coefficient of whatever the nth term is n factorial. Oh, sorry. Right. Yeah, it's n factorial c to the n. And that's whatever my c is going to be. Okay. So this c is basically, this is this part right here. So that's that f of a to my nth power. And I would divide it by the n factorial. And that's going to be whatever the coefficient is in front. Just trust me on this one.
Ideally, I was debating whether I should write everything so that it makes sense, but it's a lot of writing.
Don't write it all. That's fine. You can, like, you don't have to, because literally this slide's going to give you the answer, the format of it. So what that all was, one of the annoying mathematicians of the past, Mr. Taylor, figured out that the power series, he can represent it with the derivatives. So the Taylor series is what it's called, is the f of x. So this is my power series. And this is the coefficient, is whatever the derivative of whatever term we're in. So if we're looking at the first term, it's the first derivative. If we're looking at the 20th term, it's the 20th derivative. A over whatever the same thing. So if it was the 20th, it would be the 20th derivative at A over 20 factorial, which none of us want to figure out. Which is okay. So this is what the Taylor series ends up looking like. He figured out that any function over here, as long as it can be represented as a power series, we can represent it with this function to figure it out. And that allows us to approximate pretty much any function. Okay, because most functions I can somehow finagle into a power series. At least all the major ones that we're going to need to figure out. So this right here is known as the Taylor series. The one underneath it, you don't have to write out. It's literally just expanding out this. I gotta minimize the bottom piece so you can write the bottom one. So this is Taylor. Not Tay-Tay, Taylor. And this is McLaren. Or, hold on, let me make sure I spell his name right. M-A-C, because I always want to forget the A. And that's McLaren. What's the only difference between Taylor's and McLaren's? Or what's the big difference? Yeah. So McLaren figured out that, well, if you plug in the 0 for A, so instead of it being centered at some arbitrary number, if we center it at 0, it simplifies most of the stuff and still gives us a good approximation of our functions. So these two series here, this one and this one, we're going to use a bunch. So what the Taylor and McLaren series allow us to do and allow our computers to do is to estimate the vast majority of our functions. So when you type in, like, you can figure out what sine of pi over 2 is. Like, we know that. That's 1. We can get that answer easy. We have the unit circle. But what if I wanted you to find me sine of pi over 57? Not as easy to do. Pi over 12, we might be able to break things down using half angle formulas and stuff like that. There's ways to figure it out. Depending on who your pre-calc teacher was, depending on how much they wanted to torture you, you might have to do a few of those. But the vast majority of the time, you're not going to use those to calculate out. However, we do need to find that sometimes. We need to find the sine of 12 degrees sometimes, right? And we plug it into our calculator, we get an answer. How does the calculator get that answer? It doesn't know sine. What it knows is it knows the power series. It knows that summation that goes along with it, because it can calculate that using addition and subtraction. Okay. So let's look at a few of these. So one of the main, so we've got 2 irrational numbers that we see a ton of, pi and e. Okay, those 2 irrational numbers come up a lot. So being able to estimate e and find a value for an exact value for that answer would be helpful. All right, and that's why there's a button in your calculator that says e, because it has this built into it. It has the summation built into it to be able to do that. Same thing with pi. So let's look at e. Now it says we're going to use the McLaren series, not the Taylor series, which means we're going to use the zeros. Come on. Here we go. All right, so we've got our, so we know that f of x is the summation of f to the n, or f to the nth derivative, 0 over n squared. So f of x equals the summation of n equals 0 to infinity of f to the n of 0 over n factorial x. Oh, x to the n. There we go. So if we have e to the x, what's the derivative of e to the x? So if f of x is e to the x, f prime of x is e to the x, right? F double prime of x is e to the x, correct? And this never changes, right? Okay, so if I plug in 0 to e to the, what's e to the 0? So if I plug in x equals 0 to this, that's 1, that's 1, and that's 1. So basically, it's always going to be 1, correct? That's what makes these things so, like the ones that we're going to look at today, so useful, is because the actual derivatives come out to be things that are easy to find. You could technically do this with a lot of different things. The derivatives just aren't always easy to find to come up with that pattern. So we now know that that is always 1 over n factorial x to the n. So that's what e to the x equals. The next thing that's actually really important to find in these is our radius of convergence, because that tells me what values I can plug in for x that this equation would work for. Okay. So how do we figure out radius of convergence? How do we figure out when convergences happen? What was one of those wonderful, nice little rules that always works that helps me figure out convergence? Starts with an R.
I would also ask you. Not the ratio test?
Yes.
Thank you.
There you go. You asked your Gene, you got your answer. So the ratio test. Because if it was less than 1, so between 0, basically between 0, if it's less than 1, it is convergent. If it's greater than 1, it's divergent. And if it equals 1, we don't know. So ratio test, a to the n plus 1 over a to the n. And it's the limit as n goes to infinity. So we have x to the n plus 1 over n plus 1 factorial. Actually, I'm just going to write this as a multiplication and flip it over. Times n factorial over x to the n. So remember, we can move these, put the factorials together, put the other ones together. So x to the n plus 1, I can rewrite as what? Right, x to the n, x times x to the n. N plus 1 factorial, I can rewrite as what? And then n factorial. Which means I can cancel that out. I can cancel that out. So this ends up equaling x over n plus 1. So as the n gets increasingly large, this whole thing is going to what? That's going to 0. And 0 is always less than 1, correct? So this is always convergent. So the interval of convergence is negative infinity to infinity. So this function works for any value of x. So function was 1 over. All right. So give me a number for x.
12.
Okay.
That's my favorite number.
Okay, so here. Not gonna zoom in, but. So e to the 12th power is, yes, 162,754. So I replace x with 12. Is that the same answer?
No.
No. I did 10 terms. So the question is for it to work, I might have to do a bunch of terms, right? 10 might not be enough. If I did 50 terms, it's now the exact same answer. Okay. The other cool thing is if we change these to x, so if we use x for this and x for this. So you actually can see they're literally the same line.
Cute.
So, but look what happens. Notice how it gets down here, it shoots back up instead of falling out. So at some point over here, the values over here won't make sense anymore. But if we were to increase that out, we start to get something that then again works. And I actually can't calculate out that far, but we get something that again works as we go further and further out. If I change it to 100, it might be better. So you can start to see how it breaks down a little bit further down. If we change it to 200, it goes further out. If you change it to 300, it goes further out. Okay. So we just have to add more and more terms to get those, but this side always works. Okay. Does that make sense? This is how your calculator calculates E. That's how a computer calculates E. The calculator knows that. It knows, okay, I just plug in a number here and do the summation of it. Because it can do that easily. Calculators are really, really good at addition. Not very good at anything else. So that's E. What's another one of those functions that works that the derivative is really easy for us to calculate and figure out? Huh? There is another one that tends to repeat itself. Sines and cosines. Right? What's the derivative of sine? What's the derivative of cosine? And then negative cosine, and then back to sine again, right? So it repeats. It's got a pattern. We have a pattern, we can figure something out. We can make it, we can actually look at that pattern and figure it out. So let's find it for cosine. So do the same thing we just did. So you've got, remember, f of x equals, together. All right. So do the first 4 or 5 derivatives for cosine and see if you can figure out a pattern. Oh, I didn't switch back over. Thank you. There we go. Now that I have all this wonderful stuff written down here. What's the derivative of cosine of x? Negative sine of x. What's the derivative of negative sine of x? What's the derivative of negative cosine of x? And then it goes back to cosine of x. If we plug in zeros, so x equals 0, because that's what we use for the Maclaurin series. What's cosine of 0? What's sine of 0? Cosine of 0? Sine of 0? Cosine of 0?
Simon's for PQP.
Huh? Sine of 0? So, and if I did it again, I get 0 and then -1. So, do we have a pattern form? Huh? I'm like, wait, yes, we do. You could figure this out to whenever I feel like telling you to stop. All right, what's the pattern?
Back and forth between 0 and 1 and -1 and 0. That's what's happening.
All right, so let's write it out. Okay, because sometimes writing it out actually will help us figure out what's going on. So the first term is going to be plug in 0, you get 1. Actually, we get 0, sorry. So you plug in 1, first derivative is going to be 1 over 1 factorial x, right? The next one's going to be 0 over 2 factorial x squared. And then minus 1 over 3 factorial x to the third. I'll screw that up. Hold on. Oh, I can screw that up. Hold on. I didn't write anything. What are you talking about? It was never there. I forgot cosine was my first. This is 0 derivatives. So we've got 1 plus 0 over 1 factorial x to the first plus -1 over 2 factorial x to the second plus 0 over 3 factorial x to the third plus 1 over 4 factorial x to the fourth plus 0 over 5 factorial x to the fifth, and so on. Do I need to write the zeros? No, because they're gone, right? So if I get rid of that one, and that one. How can I get those terms? So let's look at the exponents. It's basically 0, 2, 4, and the next one's going to be 6, right? So it's all the even ones. So that's going to be x to the 2n, because that's going to give me all the even ones, correct? Okay. What about the bottoms? That's 0 factorial, 2 factorial, 4 factorial, same thing, right? So it's 2n factorial. What about the top? We go 1, -1, 1, -1, so it's swapped back and forth, correct? So that's negative 1 to the n minus 1? Or, sorry. Actually, just n. Because we wanted to start off with positive 1 first. So we now have cosine. So what was it? It was x to the 2n, right? Over 2n negative 1, correct? That was what it was? Yes? Yes. All right. So if you look at this, that looks like a pretty good approximation of cosine, right? I think it was there. So whatever number I want to plug in for x, let's do, what was one? Pi over 57, did I say? There we go. So the concept that we were looking at before with the power series is designed in a way that helps us figure out all these ones that aren't necessarily the easiest ones to calculate. All right, if you want to take a picture of something, take a picture of that.
Going on the note card. Oh, yeah.
You won't need them all. You won't need them all for your test. So we found 2 of them. We found e to the x and cosine of x, but that's the rest of them. So you've got the ln one that we did actually last time, the ln 1 plus x. Yeah, arctangent in there. And then you got the binomial expansion, the 1 plus x to the k, which is used a ton in probability, in statistics. Everybody got a picture of it somewhere? Okay. All right. So now, the nice thing about these are, if there's a nice thing, is that we can use these series to find other series. So let's say I wanted to find x cosine of x. So if that's my f of x, and I want to find the series for it, what was the series for cosine of x? That was the one we just did.
-1 the n over 2n factorial times x to the 2n.
Whichever way you want to write it. So that was my cosine, right? I want x times that. So if I can replace cosine of x with that, this becomes just x times -1 to the n. Can I bring the x inside without changing the problem? Because I don't want to have multiple x's. So does the x have an n on it? No. So if I bring it inside, it's not going to change anything because it's not something that's being added multiple times. It'll be just multiplied by whatever was there. So I can bring that inside. If I'm bringing it inside, I have times x inside now. How can I put that together with this x? Plus 1. You're almost there. Yeah, remember the exponents, you add the exponents. So f of x, x cosine of x, equals the summation of n equals 0, -1 to the n over 2n factorial, x to the 2n plus 1. What about this one? Oh, yeah. Give me 1 second. That's what it is. So now we have those. That's why I said take a picture of those that thing, because those basically can become things that you just put in there. So this one is f of x equals ln of 1 plus 3x. This is ln of 1 plus x. So use this to give me the summation for the new one. This one? Oh, this? It is the hold on, I'll give you the exact name for it. I don't remember the exact name of it. It is the binomial series. So in I've used it probably in statistics. Basically, what it allows you to do is to figure out the coefficient of any term in a binomial expansion. So if you had like x plus 1 to the 20th power and I wanted the fifth term, this will help you figure out the fifth coefficient, the binomial series. All right, so what do we got in this one? What's the change? That, right? So x is 3x squared. So if I change the x, to 3x squared, that's what I get. So we can multiply or distribute out the n to both things so we can get the 3 out by itself. And that's what you get. So basically, any function that I have that I can somehow make into one of those Maclaurin series that we have, I can now do. So why teach this in calculus? What's the integral of that?
I don't know.
Why?
It's an explanation.
I'm like, that looks really straightforward and simple, really. It's not, that's just an e to the negative x squared.
The one who wrote the freaking textbook, brother.
Huh? So how'd you do it? No, how'd you do it? What's the method called? U substitution. All right. So you said u was negative x squared, right? Okay. So what's du? Negative 2x dx, right? Okay. So if I move this over here, I get negative du over 2x equals dx, right? Okay. But now I have, so this is what now I would have. I'd have negative 1 over 2x e to the u du. So I have a u and an x in my problem. As far as I know, you don't know how to do multivariable integration at the moment. So this would be fine if it was the integral of x e to the negative x squared. Because then I have an x that I can get rid of.
So for functions, you see it. multivariable.
No, you actually still can't do this problem. Because the concept of u substitution doesn't work. Like multivariable allows you to do like, remember the differential equations we did when you took the integral of x squared plus y squared and you had that piece in there? That's the beginning of multivariable when you're looking at multiple variables when you're trying to do it. So multivariable integration doesn't work with u substitution like this. So even at that point, this still would work. Right. So this one you can't do. Okay. You cannot integrate this. If you try to integrate this as what's known as a non-elementary solution, if you try to do this in Symbol Lab or anything else like that, it's either not going to do it. Actually, this one it probably wouldn't do it. And if you try to solve it for a definite interval of like 0 to a number, it would give you one with like the i's in it because it doesn't work. Okay. So the question is, well, we still have to be able to do stuff like this. So how could we do it? Well, let's think about what we just did. Okay. We have a way to estimate e to the negative x squared. Okay. So actually copy this one. Actually, let's do this. We don't want to have to do this over. All right. So what was the summation for e to the x?
One over n factorial times x to the n.
Right. Very first one we did, right? That one. All right. So if x is now negative x squared, we would just replace the x with negative x squared, right? So e to the negative x squared n equals 0 to infinity of negative x squared n over n factorial, which is negative 1 to the n x to the 2n over n factorial. Right? Okay. So give me the first 5 terms of this. So if I plug in 0, what do I get? So I get 1. If I plug in 1, what do I get?
Negative x squared.
If I plug in 2, what do I get? Two times 2 is 4, so x to the 4th over 2. Right? Okay, if I plug in 3, what do I get?
So it's 6 over 3.
3 times 2 times 1
Wait, no.
is 6.
6.
If I plug in 1, 2, 3, 4, 5, those 3, 4 to it, what do I get? We're plugging in. We're basically expanding out the series. So x to the 8th over 24. And I said we're going to go to end of 5. So if I plug in 5, I get x to the 10th over 120. And that keeps going. Correct? Because we just stopped at the n is 5. All right. Can I find the integral of that? What's the integral of 1?
X.
What's the integral of x squared?
X cubed over 3.
What's the integral of x to the 4th?
X to the 5th over 5.
So 10, all right?
Yeah.
Okay, integral of x to the 6th?
X over 7. So that would be 32 on the dot.
X to the 8th over 24?
7 times.
I'm just going to leave it as 9 times 24. And this next one's going to be
11 times 120.
huh? No. Actually, you want to leave it.
We
Because
left all of them.
I changed them afterwards. You want to leave it because this goes on forever, right? We're not going to be able to do this forever. So what do we actually want? We want a pattern. Okay, so we're looking for a pattern. If we can find a pattern, then I can set my equation. So what is the pattern for this? So the first term is just x. And if I write this so I have something underneath it, it's x to the first over 0 factorial. Because 0 factorial is 1. Okay, so that's 1, 3. So the x's are 1, 3, 5, 7, 9, 11. Those are all what? Odd numbers. So how am I going to get an odd number? Always.
To the minus 1.
Yep. X to the 2n minus 1. Will always give me an odd number, right? So if I plug in 0, that's not going to work. But if I plug in 1, it would, right?
Yeah.
But if I change that instead of minus 1, if I change it to plus 1, that would also work at x equals 0, right? That would work with n equals 0.
Yeah.
So let's do that. Let's do it 2n plus 1. And we'll set it at n equals 0. All right. So the next thing I've got is it's alternating, correct? So that's going to be negative 1 to the nth power. That'll give me my alternating. Now, how am I going to get the bottom? So I've got whatever the n is, right? Still on the bottom. So 2n plus 1, because that'll give me the 1, 3, 5, 7, 9, 11. That'll give me the same thing as the exponent, right? And my n factorial is 0, 1 factorial, 2 factorial. That's 3 factorial, right? Right. So it's still the n factorial. Because it's 0 factorial is 1. 1 factorial is also 1. 2 factorial is 2. 3 factorial is 6. 4 factorial is 24. 5 factorial is 120, which was those numbers that I got down the bottom. So
This might be a dumb question, but why is 0 factorial 1? Is it, should I just accept it?
You sure we can talk about why 0 isn't 0?
honestly,
How much time do we have left?
Sorry, that was weird.
It's okay.
honestly, I don't remember off the top of my head. I'm sitting there like literally like I remember learning this at one point. I honestly don't remember why. It's something to do with the pattern forming of like because
So what about
no, it's because in multiplication, if you're multiplying nothing, it's automatically assumed to be 1. Like when you multiply something by like and you get the exact same thing, the identity is multiplying by 1, not 0. So since you have 0 factorial, so technically you're not multiplying anything, so that would be 1.
so like it remains
Okay.
infinite?
So like 0 factorial times 5 is going to still be 5 because you're technically not multiplying that 5 by anything. That's why it's
Okay.
listed as 1. That's the easiest thing. There's a way more complicated explanation, but that's the easiest way to think about it. All right. We have our answer for the integral of e to the negative x squared. The integral of e to the negative x squared is this. So now whatever x is, I can figure out what this is. That's literally would give me that integral to infinity. So using the summations and using the Maclaurin series, we actually can find the integral of things that you wouldn't know off the top of your head, in essence. So if I wanted to find this from 0 to 1, you're plugging in the x at 0 and 1. So we'd plug in 0 for that for x, and we plug in 1 for that. We could figure out those pieces, maybe not out to a million terms, but you could figure out enough terms to find your actual answer. Okay. All right. I'm not doing that. Let's do. Let's do this one. All right. So every one we've done so far has been a Maclaurin series. So the question is why do we have a Taylor series if the Maclaurin series always works? So you're always approximating a function with this. They're never going to give you the exact answer. Most times we're not going to want the numbers out far enough that it's going to melt. So, but as you get further and further away from zero, the Maclaurin series is centered at zero. So the further you get away from zero, the more inaccurate the answer is going to be. Okay. So if I wanted to find this function and I want to figure out somewhere between 7 and 9 is going to be my x. Okay. I'm not going to want to center it at 0. I'm going to want to center it at 8 instead of at 0 because 8 is going to be in between the values that I'm going to be looking for. So remember that mean value theorem where it's like we're looking crossing 0. If we find things on either side of it, we can get closer and closer and closer. That's in essence what this is doing. So we don't want to necessarily always center them at 0. We want to be able to center it at different points. So the Taylor series basically allows me to do that. The Maclaurin series is just a special case of it. So let's figure out this series. So your Taylor series, if you remember back from the very beginning, the very first thing I did. Hold on, scrolling back. So I'm going to copy it back over. There we go. Taylor series. All right. So A in this case is going to be 8 because that's my center. That's what I'm looking at the center for. So in this case, A is 8. So f of 0 of 8 would be the no derivative, correct? That's basically just f of 8. So it's the third root of 8 is what? 2. The first derivative at 8. So we first have to find the first derivative of the square root or the cubed root of x. So the cubed root of x is x to the 1/3. What's the derivative of x to the 1/3?
1/3 x to the negative.
Yes, remember we bring down the exponent and subtract 1. So that is 1/3 x to the 2/3. So what's the 1/3 times 8 to the 2/3? So what's the cube? The cube root of 8 was 2, right? 2 squared is times 3 is,
12.
so it's 1/12. Okay, if I find the next derivative of that one, what do I get? Bring down the exponent, subtract 1 again. So negative 2/9 x to the negative 5/3. So 1 over. Not 1 over. Negative 2, 9, 8 to the 5/3. So cube root of 8 was 2. 2 to the 5th is 2 to the 5th. You should know 2 to the 5th. 32. 32 times 9. That you're probably not going to know off the top of your head. It's negative 200 over 288, which is negative 1 over 144. All right, and we can keep going, but we're not going to. Because not every series, like the ones that we came up with, are going to have a nice pattern. This is one that does not have a nice pattern. We're not going to, everyone that you're going to have to add, you'd have to come up with the derivative and figure that piece out for it. All right. So in this case, we've done what's known as the Taylor. We're going to do it to the second. So we're just doing just the second derivative. So that's how you write the Taylor series, the second degree Taylor series. So my first term is 2. So it's 2 over 0 factorial x minus 8 to the 0 power. So gonna out of the row if I keep writing it there. I'm going to rewrite the exact same thing. Don't work out. I just need. Plus, the next one was, what was it? 1 over 12?
Yeah.
Yes, 1 over 12. Sorry.
Does my input mean nothing to you?
No, it does. For some reason, it just caught my head. I was like, wait, I'm missing a term between it, but I wasn't. And then the next one is negative 1 over 144, 2 factorial x minus 8, the second power. So this whole thing here just becomes 2, 1/12 x minus 8 minus 1 over 288 x minus 8 to the second power. So that is your second degree Taylor series of the cubed root of x. Okay?
So the test would we default to second degree Taylor series?
No, it would tell you.
Okay.
So it would say find the second degree. So actually, did I copy the whole thing down to this one or not? It did. See, it says Taylor polynomial
Oh.
2. I'm like, wait, I thought it said that. Yeah,
I
it'll.
just didn't know what that
No, no,
meant
it's fine.
because it looked
Yeah,
like gibberish.
Right, and now you do. Yeah, it'll tell you exactly how far out you want to go. Second degree polynomial means we do to the second degree. If you look at the answer at the end, what was the degree? 2. So if I wanted to do a third degree, I would do one more term, because that would have to be a third degree. So the thing is, like, okay, is this going to give me the exact answer of the cube root of x? Yeah. So if we look at this, so let's see if I can actually do this right. Nope, it's not going to like that. Okay, fine. All right. So that's the cube root of x. And we've just said it was, okay, it was 2 plus 1 over 12 x minus 8 minus 1 over 288 x minus 8 squared. So that's that's the cube root of x, and this is my approximation. Is this a good approximation of that curve? It's like, for the vast majority, no. Right through here, yeah. And if we're looking at it, remember we were looking at between 7 and 9. If we look at that, that's a pretty good approximation of what that is. Okay, so that's where the centering comes into play. If we weren't centering it at 8, if we were centering it somewhere else, it would be a good approximation at that point. Okay, so now we can plug in any value between 7 and 8 here, and it should give me a good answer. The answer should be very similar to those. So if we wanted to plug in, say, 7.5. And that's pretty close. It's within a couple hundreds. Oh, it's 5.5? You're right, 7.5. There we go. Even better. Way closer. Okay? So that's a really good approximation of it. And while I don't think anybody in here can give me the cube root of a number cube root of 7.5 off the top of your head, right? You wouldn't have been able to come up with that prior to this. I'm willing to bet if I told you to plug in 7.5 into this equation right here, you'd all get me an answer. Because that's just basic algebra. Actually, it's basic arithmetic. Okay? So this is where these types of problems come into play. It allows us to approximate those values to a relatively decent value. Like that's accurate to within what, 10,000s? If you round to 1,000, because that would go up to a 5. But that's pretty accurate for most situations. And we only did 2 derivatives to figure that out. So the question comes up is like, okay, how accurate do we need to get? So Taylor, that wonderful Taylor again, way more famous than before Taylor Swift, came up with what's known as his inequality. Taylor's inequality. So what Taylor's inequality gives us is it allows us to figure out how accurate the answer is going to be. It'll also allow us to figure out which value we need to get to a specific, to be accurate within a certain number of decimal places. Okay. So M is always one more derivative than what we did. So we did the second derivative, right? And my second derivative, so we're going to look for my third derivative for this one. So the second derivative was negative 1 over 144 x to the negative 5/3. So what's the third derivative? We'll just figure it out. There you go. We pull down the negative exponent, right? And then it's going to be x to the what?
Uh, 8 terms.
Just add 3. So this is going to be 5 over 300, 420, 432. Where did you get 10 over 27? Oh, I know why we did that wrong. It's not 1 over 40, 144. That was when we plugged in the number. It was 2 ninths. It was negative 2 ninths. We plugged in the number there. That's why. Like, wait a second. They got a number that's way off of what I've got. That's way better. You didn't catch those mistakes. Catch all my little ones.
Gee.
All right.
Don't blame me. It's not my fault.
All right. So we have their third. Yes, we have our third degree now, or our third derivative. So I know that m value is going to be somewhere between the 7 to the 8 thirds. So I have 10 over 27 times 1 over 8 to the 8 thirds is less than, obviously, the 1 over 7 to the 8 thirds. And nobody's going to figure that out by the hand, so don't worry. If you calculate that, you get 0.0021. Yes. So I know it's going to be somewhere in there. That's my m. Because we just figured out this piece right here. So my remainder of the second degree is less than or equal to 0.0021 divided by n, which in this case was 2. And we're going off 1, right? Because it was 7 minus 8 to the 2 plus 1. Approximately. So I'm going to be within 4 10,000ths, which we were when we plugged that number into the calculator. So using this formula, we can say, okay, well, if I wanted it to be more accurate, if I wanted it to be within 1,000ths, well, I have to go to the third. I have to do a Taylor's of the third degree instead of the second degree. And that would give it to me within 1/10,000th of a place, or probably even more accurate than that. So that tells you how far out you have to go to get the actual answer you want. All right. Not that I'm going to do this but I want to show it because it's kind of cool. What's it look like? It's an eyeball.
Oh.
It's actually a spherical lens, which is what your eyeball is. They actually have used these equations. So Fermat came up with a good theory, and Gauss came up with a better one. But they actually use Maclaurin series and Taylor series to estimate where the actual point is on the spherical lens that you're going to have everything go to. So depending on how the lens curves, it focals it in on. That's why if you wear glasses or contacts, it's because the focal point at the back of your eye is not in the correct spot. So the lens that goes in front of it curves it in differently, so that actually hits where your eye is. That's where your prescriptions and stuff like that changes, because over time, that changes. As you get older, it changes because your eye actually changes shape. So these wonderful formulas all do this. Yeah.
Why is the prescription for my glasses different than the prescription for my? Is it just that small distance?
Closer to your eye. Oh yeah, it's closer to your eye. It's way closer to your eye. So that's why, even reading glasses and stuff like that are designed, because if you're closer, if you look, that S is that point of the actual whatever this. I think they're using sound waves in this picture, but be light or anything because it's all just a wave. So wherever that is, it changes how far back it has to actually curve it to come in. So if you're wearing reading glasses, it's a stronger curve because it's closer to your face, so it has to curve it in faster or a steeper curve. So that's why those lenses are things. Contacts are a lot closer to your eye, so that prescription is going to be a lot different than glasses, which are further out. And that's why even if you put your glasses down here as compared to closer to your face, you'll change the actual curve, and things will get either blurrier or.
Yeah, I had to change
Chris?
contacts. I can't walk up and down the stairs.
Yeah.
If I look down or up away from the lens, the stair moves and it falls.
Well, that's like with reading, with progressives and stuff like that. It changes because of where the lenses are, but that's all based on these formulas. So, the other interesting is one more, and then I'll let you guys go, because this is something nobody ever thinks about. I'm going to go out on a limb and go, nobody in here is a flat earther.
Actually, I believe the Earth is flat and that you can fall right off the edge.
Very cool. Okay, good. Here's the if you're designing a road, anybody know? So in Death Valley, California, there's a road that is 200 kilometers long. Okay, it's actually slightly longer than that, because over that 200 kilometers, the Earth curves. And because of the curve, it actually has to be longer than it would be if it was just a perfect 2,200 kilometers. So, and one of the problems that the book has you do, actually, I put this in my book too, or a very similar one, because it's actually a really cool problem. So the problem was you got to figure out, I just put in the problem to actually do it. I gave them the formulas. Go away. There. So that's the formula that's used to figure out that curve. Let me see if I can shrink this a little bit. Go this way. There we go. So this is the formula to figure out that curve. Because in essence, it's the arc length that's there. And using a Taylor polynomial that we just figured out, this is the formula that the surveyor and stuff like that would actually use to do it. They don't need to plug in this whole or crazy thing. They would just plug in the length of the road, and the radius of the Earth is known. So all they have to do is plug in the length of the road, and they know how much they have to correct by over that distance. Smaller roads, obviously, the correction is not going to be as big, but the longer the road goes, the more that correction is going to end up having to be. So things like that you never think about, because it's like you're not doing it on a grand scale, but that actually has to come into play.
Like, I don't know the answer,
I
but
don't. I'm just kidding.
gee, thanks for the vote of confidence. Anyway,
It was a vote of confidence in myself. You said I might not know the answer to this.
I'm offended by your lack of confidence. Anyway, do they have to use like different radiuses based on like where in the world they are? Because the Earth isn't like completely
Yes.
spherical.
Yes, because you are right. The Earth is not a perfect sphere. So it actually bulges more out at the equator. So the closer you get to the equator, the bigger that radius would actually be. I don't think it would make that huge of a difference on like building scales and stuff like that. But it is things that you have to look at that. Even it's crazy sounds. Even like the Great Pyramid of Giza and stuff when they built it, because it's so large, they had to deal with the actual change in it. So, and the weight, like the middle of the pyramid's way heavier than the outside, so it's going to actually compress more than the things. Like these are the things that they take into account, which amazes me that they were able to do this like 5,000 years ago. So, all right, we're done with Taylor series. We're going to start reviewing actually the series stuff on Thursday. I will have your test posted on Friday for next week. So we'll start reviewing series stuff on Thursday. Test will be posted on Friday. We'll go over the test on Tuesday, and then your test will be next Thursday. And then we'll review for the final, those two classes, the next two classes, and your finals the week after. There's only like 3 weeks left of class. Yeah.
Wait, we're that close?
I believe I moved all the homework assignments to the 13th. It might be somewhere around there.
Yeah. Thanks.
Okay, I know I moved them somewhere around there. So make sure to get those done. If you have a possibility of not taking the final, there are still people in here that do. Make sure your homework is done the week before the final, so this way you can do exempt from the final. So other than that, any other questions? Bye, guys.